Okay, thank you. Well, thanks for the invitation. Well, today I'm going to talk to you about a differential absorption Lidar transmitter that we have developed here based on indium phosphide photonic integrated circuits for carbon dioxide sensing. Okay, this is a brief outline of the talk. I will give you some introduction and motivation. Then I will talk about the peak design of application. I will focus on the characterization of the different integrated devices that we have integrated in the chip. Then I will devote this fourth section for the carbon dioxide sensing. Then I will get out a bit of the topic, talking about peaks in space, some radiation tests that we have developed with ALTER technology, and then I will end with some conclusions on the outlook. About differential absorption Lidar, dial. This is a well-known active technique for measuring atmospheric gases such as methane, nitrous oxide, or carbon dioxide. And in the standard technique consists in sending two pulses at different wavelengths, at least two pulses, at different wavelengths that we can see here. They are tuned at different wavelengths in comparison with the transmittance of a target gas, in this case, the carbon dioxide. So we have this blue one close to the center of absorption of the gas, that is called the online signal, while the red one is outside the absorption line, and we call the offline signal. With this, you can measure the absorption along the path of the backscatter signal once it interacts with the atmosphere. This is a standard technique, and it has been used and is being exploited in different missions, such as the French German mission Merlin or the NASA Aspens mission for carbon dioxide. These lidars usually are based on pulse operation. However, there are other techniques that are based on intensity modulation, continuous wave, such as, for example, the random modulation continuous wave technique. The good thing of these techniques is that they can allow using low peak requirements, such as lasers, such as semiconductor lasers that don't have a peak power so high like the fiber or solid state lasers. And also semiconductor lasers, as you know, allow to photonic integration. That is what we exploit in this work. Okay, the random modulation continuous wave technique consists in sending and using maximum length sequence or pseudo-random sequences. And what we do is to use these signals for the transmitted signals at the different signals at the online and offline, with a delay between them. Then the light is sent to the target that interacts with the atmosphere, then it's returned to the system, and we receive similar, well, with a lot of noise more added, but with a delay of these pseudo-random bit sequences. Then, using the correlation properties of these pseudo-random bit sequences, we can obtain a correlation like this with several peaks, these two peaks that correspond to the transmitted signals, and these two ones that correspond to the received signals. In this way, we can measure the different absorption that the signals have suffered, and also the time of flight, that is the distance between within the system and the target. Okay, this was implemented using semiconductor discrete lasers in a European project where UPM was participating, and also ALTER technology some years ago. And this work is a center of focus in the development of a photonic integrated circuit to be the transmitter of one of these systems. Okay. Why? Well, because photonic integrated circuits now have reached a technological maturity and affordable cost, and they allow the development of many applications based on them. And in particular, in the case of Lidar systems, some advances have been reported in the last years. For example, this one is a coherent solid-state Lidar with silicon photonic arrays, photonic phase arrays, or this also a Lidar based on ambiguous ring and frequency cones. However, all these approaches are based on silicon or silicon nitride and need an additional semiconductor laser, an external semiconductor laser. However, indium phosphide platforms allow the integration of both active and passive devices. And in this sense, recently, well, in 2022, so in the future, a dial for CO2 has been reported from the group of Larry Coldren from Santa Barbara. That is, well, similar to what we are doing. And in this case, well, the main difficulty is that the lack of integrated optical isolators can give rise to coupled cavity effects in such a relatively complex system that involves several lasers. Okay? So what we have done is to develop a transmitter for the diode system for CO2 sensing based on an indium phosphide photonic integrated circuit implementing the random modulation continuous wave technique. We have evaluated the performance and possible detrimental issues. And finally, I will show you that we demonstrate CO2 sensing with this chip. About the fabrication, the chip was fabricated in a multi-project wafer by Smart Photonics. And it's worth noting that we have used standard building blocks. Okay? We have used BPI Photonics for the initial simulations and the initial layout design, and finally NAFTA to produce the final layout design. This is a schematic of the chip. This is with all the components. What we have is three lasers, three distributed back reflector lasers that are, well, their frequencies or wavelength, lambda 1, lambda 2, and lambda ref, are here depicted together with the absorption line. So we aim that the reference wavelength will be at the peak of the absorption line. Lambda 2 will be our on signal, and lambda 1 will be our off signal. The difference between reference lambda and lambda 2 should be around 300 or a few hundred megahertz, while the difference between the reference and lambda 1 should be 10 gigahertz. Okay. Then we have 5 semiconductor optical amplifiers that are noted here. Some are used as optical gates to control the output power of the different lasers, and these 2 are for boosting the output of the chip signals. Okay, the output is the output for the signals that we are making, that we are going to use for the diode measurement, and this output there is, well, the output for the reference signal. The implementation of the pseudo code modulation is done with the electroabsorption modulators, and we also use 2 fast photodiodes for measuring the bitting between laser 1 and laser ref, and the second is for laser 2 and the reference laser. Okay, because, well, at the end, what we have here is 2 subsystems, one for performing the CO2 measurement, and the other for controlling the emission wavelengths and stabilize them based on phase lock loops that you can see here. No? So the idea is that the reference laser will be locked with a CO2 cell and a loop to control its wavelength, and then with the internal photodiodes control the position of the other 2 lasers. Okay. About the lasers, we have used 4-section DVR lasers that they have been designed to be single mode operation. The emission wavelength is close to 1572 nanometers, so we have modified the DDR pitch. We have put also isolation sections between the different sections in order to avoid current flows. And we have included a photodiode for power monitoring. This is a photograph of the fabricated device. Okay, so here you can see the different lasers and amplifiers. So this is the electron absorption modulators and the output. And here in this side is the output ref. The size is 4.6 millimeters by 1.5 millimeters. And we electrically access the chip through 20 DC pads and also 4 RF pads for the modulation and also for obtaining the bit signal at the photodiodes. Okay. So for the characterization, we have used multi-contact proofs, like is shown here, then 2 fiber lenses, lens fibers, sorry. Here you can see the photograph. And we have used an optical switch in order to record both outputs at the same time with a OSA or with an optical spectrum analyzer with a 6 gigahertz resolution, or a BOSA, previewing optical spectrum analyzer with 10 megahertz resolution. And also, well, we have used an electrical spectrum analyzer to get the photodiode signals. Okay, all this chip is controlled. The temperature is controlled. About the results of the characterization, well, this is a PI curve of one of the lasers. Here I'm showing you the PI curve and the voltage current characteristics. Okay? And here in this graph, I'm showing you the optical spectra of the corresponding to the PI curve. Okay, and we can see that, well, that there is mainly single mode operation, but there are several wavelength jumps. Okay, the good thing is that the emission wavelength is close to 1572, and we have a threshold around 25 milliamps. This is one of the lasers. In this case, I think it's laser 1, and all lasers are working more or less the same way individually. The thing is when we put two lasers at the same time. No? For example, in this case, that we have laser 1 and laser 2. This is you can see is the same, but here in the spectra you can see in the left side laser 2 spectra, while this is laser 1 spectra. And we can see that the PI curve, the voltage current characteristic is the same, but the PI curve has changed, and also the spectra and the emission spectra of this laser 1. So, and the current threshold is preserved, but PI spectra of laser 1 is affected by laser 2, so we have coupled cavity effects. However, we have regions of stable emission, for example, in this one or this one, that may allow the diode measurement. Okay, we also have evaluated the response of the fast photodiodes. Here, what I'm showing you is the optical spectra recorded with the Brilliant optical spectrum, and here is the one recorded with the electrical spectrum analyzer. And here, what we have here are the three lasers switched on. Okay. So we have laser 1 and laser 2, and this reference. The reference also appears at the output, which you can see here. But well, we can see that there is the difference between lambda 2 and lambda ref. It can be detected at the photodiode. Okay? When we put this reference between both signals, we can also get the bit-in signals of both photodiodes. So we conclude that that is a good performance of the fast photodiodes, at least for the application that we want. However, when we try to make the reference signal close to the lambda 2, then we have observed mutual optical injection between the reference and the laser 2. So, well, in this actual version of the chip, this prevents the use of the wavelength stabilization subsystem. Okay, and you can see here that then there appear some four-way mixing effects and even chaotic behavior. So this is a problem of this, but okay, we can live with that at that stage. We also have characterized the electroabsorption modulators. This is the static extinction ratio between the voltage applied to the modulators, and we have obtained good performance with extinction ratios of -15 dBs. And we also have checked that the wavelength doesn't change, at least appreciably, with the modulation of the electroabsorption modulators. Okay. So finally, in this, I will show you the experiments that we have performed for CO2 sensing. This is a setup in fiber emulating the Lidar configuration, where we are gathering the signals for performing their measurement. Then a part is divided in order to have the transmitted signals and the received signals that go through the CO2 cell, and also a fiber spool, and then a mirror, return back, and gather with the photodiode. We have used, for the generation of the pseudo-random code, we have used a system on a chip FPGA with digital analog and analog to digital converters working at 100 megasamples per second. And we have used 8-bit maximum length sequences at 12.5 megabits per second. With this, well, we will have a correlation that in this case we have calculated in MATLAB, and using this expression, okay, these two comes by the two, by traveling in the path 2 times. Okay. About the experiments, well, we have noticed in the optical spectra that the line width has increased a lot with the modulation. Especially in the lambda-1 signal. But, okay, this can be a problem because in these dial systems, the line width should be very well established. But in this case, as lambda-1 will be in the low absorption region, is not affecting us too much. And here, what I'm showing you is the cross correlation obtained with 50 averages. So this is a total acquisition time of 1 millisecond. And we are measuring the differential absorption optical depth, that is the difference between absorption due to the gas, in 0.5 dBs, that is in agreement with the specifications of the gas cell. And also, we have checked this using tunable laser absorption spectroscopy. So we can say that the CO2 sensing with the chip has been demonstrated. And also, we have performed experiments changing the temperature of the chip, so we can tune the both signals at the same time, and performing a profile of the absorption line. Like this. So these measurements are in agreement with this tunable absorption spectroscopy that we have performed also. So, well, that's all in that part. Now I'm going to talk about some radiation tests that we have performed to some chips, previous chips, in order, because the idea is that at some moment these differential absorption Lidar transmitters could be eventually in a satellite. And well, this was done in collaboration with ALTER technology, and we made some tests, radiation, gamma radiation and proton radiation tests for the chips, using typical values for a space mission. In particular, the gamma radiation was done here in Tiamat, close to our building. And then this allows us to make measurements in the windows between the sessions of radiation, okay? And well, here I'm showing you this. What we did here was to measure PI curves of these 4-section DVR lasers. And here I'm showing you the PI curve at different windows. And we can see that they are not exactly the same, but the threshold is maintained and the power is also maintained. We suppose that they are not exactly the same because there are other things or conditions. For example, it was in summer, there was it was really warm in our lab. So this could be the reason of this. And well, we have also performed the same with the proton radiation, but the proton radiation was done in Switzerland, so we can only measure before and after. And we can see that, okay, there are small differences, but the current threshold and also the power are more or less the same, and also the voltage current characteristics. Okay. So with this, I will summarize. Well, the conclusions are that we have designed and fabricated a differential absorption Lidar chip. We have characterized the devices integrated in the real peak, and well, we have found some problems that we expect to solve, but we have demonstrated CO2 sensing, and we have performed some successful initial radiation tests. The next steps are to understand these dynamics induced by the coupled cavity effects, to improve the design and fabricate a new version of the dial peak, to demonstrate the wavelength stabilization subsystem operation, and perform realistic dial experiments. Okay, so this work has been submitted to the Journal of Selected Topics of Quantum Electronics. If we are lucky, you will find more details on that. And has been developed with the help of with Clara, Victor, Alicia, Manuel, and Ignacio, and on ALTER with David and Juan. So thank you for your attention.
Well, thank you very much, Tony. Now we have time for some questions from here in the room.
Thank you. I think you really need the optical isolators to be integrated in the peaks. It is possible to do that, but the problem is going to do that in the future, or there are
well, we think now they are not available, these optical isolators, but there are several strategies to have them in the future. But well, we think that our we can say our way to improve that is to avoid the internal reflections of our, for example, our couples are having internal reflections that we can avoid with a better couples. But okay, I think that there is a lot of work on this direction, trying to maybe not in indium phosphide or silicon, but maybe with polymers, something heterogeneous, or using other platforms in the indium phosphide, for example.
Thank you very much for your talk. And actually, I wanted to ask you if you know what happens, because I saw you showed what happens when one of the lasers is switched on, but you have the other already on. And I wanted to know if you know what happens if you switch them on at the same time, because usually cross-coupling between lasers depends on the history of the switching.
No, I don't know, because usually we don't measure at the starting point. We don't measure, but it's interesting.
Yeah, because actually, if we have SOAs for the lasers, that can work to help you, but only if you switch them on at the right time, because that will increase you will have lower gain at the end of the SOA, but only if the laser was on.
Okay.
Otherwise, if the otherwise was on, then the SOA is working reverse, and it helps the enhance the back reflection.
Okay. Okay, so you know, we didn't know.
Yeah, now it's a whole world.
Yes, we noticed that.
Any other questions here?
Amazing work. First of all, I'm quite amazed. Congratulations for what you're doing there.
Thank you.
When it comes to continuous wave Lidar in certain conditions, special space, the integration of the external amplifier is the secret in the whole source. I would like to ask you, and also the other people in the room, if there are plans, activities, to do a demonstrator already with the external amplifier.
Well, in our case, at the moment, no, but we are open to follow up this activity. And well, Alter, I think that they are working on Lidar also, but you should ask them because I am not aware of this.
I open the question to the Alter representatives in the room. I don't want to do the chair session. I don't want to see the Alter from the beginning, not just 2 years. Thank you, Jose.
I answered definitely yes. Okay. I think we will have a later turn for my colleagues from Marvel, but as we are in what we call a specific integration of the photonic. So as Antonio said, in the outcome of the development, we will have to study what are the limitations of the regarding integration zone. But yes, definitely we will get to offer this innovation. Yeah.
Show more questions.
My question is regarding the thermal photonic. You have a DVR laser and a SOS at the DVR open. How do you deal with this effect? Because we're going to get in the SOA. This SOA is hitting, and this DVR is very close to the SOA. When you are in the discovery, this heating generated by the SOA will affect the DVR. How do you deal with that? Because this effect makes that the wavelength generated by the DVR will be maybe back and forth. Okay. You will have a decrease of the decrease that will alter. How do you deal with that?
Well, we didn't measure this. Well, I saw a talk of Guillermo about this topic, but our lasers are in continuous wave. So we expect that at some point it arrives at some thermal equilibrium, but they are more in your experiments. I think that they were really close together, and we are at least each laser or each SOA is around 300 microns of separation or something like this. So it can be, I suppose that there are some, because there are a lot of effects there. I don't know what happens really, but in our case, I think that they have not a big impact, or I hope.
Okay. I thought that you were talking about that the use of ELC.
Sorry.
So the wavelength of the system. We're using a PLL. I doing the second or the third slide.
Let me see. The third slide.
I don't remember what you did. You mentioned that you were using a PLL.
No. This was okay. We are not using it right now because of the problems that we have show you. So the idea is to use this phase loops in order to tune the different wavelengths, but not at this moment.
Because my answer was focused on the okay, introducing computer peripheral, what is the maximum frequency rate of the optical data we're achieving using this CLS? Because I think that the argument expert in this but according to the feature on the right side of top right side,
Yes.
if you have a lambda 2, lambda 1, and if this have a free, maybe the measurement will be also to change because we are changing a specific material.
Mhm.
Then we are even measured that for each material is going to get wavelengths. Maybe you have a different response. Then we will see notice the material you want to aim. Maybe you will be measuring another different material.
Well, but the thing is that we have choose a wavelength absorption line that is in principle there is free of other gases. We can say that we can go in these 1572 nanometers, or you can go to 2 microns. Well, with indium phosphide not, but you can go with other technologies to this other wavelength.
Another question is, do you think that the optical values from each laser affect the measurements?
Yes.
Or do you need a very narrow optical values or implement a very good
Yes, definitely, yes. We need this. This is not very wide, so I think it was 3 gigahertz or something like this. This line, so we need something really narrow.
Okay. Thank you very much.
Okay, you're welcome.
Okay.
Okay.
Then thank you.
Okay. Thank you.